Welcome to Bart's Videos. We're doing section 4.2, kinetic energy and the work energy theorem. I'm going to move through this very quickly to keep the video short, so please pause whenever you need to start copying things down if I'm moving through it too quickly. I apologize for the sound of the hum in the background. It's probably the air conditioning being picked up by the microphone. Alright, so work done on an object causes the speed to increase. Specifically, the object gains kinetic energy. Now, I derived the formula. You're going to remember it right here. EK, kinetic energy, is equal to 1/2 mv squared. Now, let's derive that. We can get there right from our work equation. So, work equals Fd. Now, you're going to remember it's cos theta. But we're going to assume theta equals 0 degrees. So that just goes to 1. Then we're going to replace force, F net equals ma, right? That's Newton's second law. So that's how we get there, that replacement. Well, A, we can rearrange for A using the fifth kinematic equation right here. So if we take v2 squared equals v1 squared plus 2ad, rearrange for A and make that substitution, that's how we get there. And then the distances cancel out. If we distribute the mass into the formula, then we get mv2 squared over 2 minus mv1 squared over 2. If we assume that v1 equals 0, this got, my palm probably got rid of it. If we assume v1 equals 0, then this goes away. So our initial velocity is 0. Then that will tell us the total work required to bring that object from 0 up to that speed. And so that's how we got here. And then we're just going to replace W with EK, and there we go. We have our formula. And just to note then that any work done on an object will produce a change in kinetic energy. Wonderful. So we're going to go through and just show a few examples. And I just did this on the fly, and I haven't actually worked out numbers. So that'll force you to slow down and actually do some calculations and compare with everybody to see that you know what's going on. We have a car has a mass of 1.5 times 10 to the 3 kilograms and travels at 85 kilometers an hour. Calculate EK. So I state my givens. That's like normal right here. So here are my givens. And then I have EK equals 1/2 mv squared. Sub the values in. Boom. There's your calculation for kinetic energy. There's the moving energy. For example 2, we have a 1.4 kilogram rabbit, has 96 joules of kinetic energy. What is its speed? And so again, we state our equation, but now we're going to rearrange and solve for velocity. So I multiply both sides by 2, and then divide both sides by m, and then square root both sides, and that's how I get this version of the formula. And then I just sub my values in and solve for velocity, and I'll leave that for you to pause the video and try it there. For example 2 here, for example 1, sorry, we have a blue whale of 1.5 times 10 to the 5 kilograms. It's swimming at 6.1 meters per second, and it increases its speed to 12.8. So calculate the work done by the whale. So this is referring back to that formula that work is equal to the change in kinetic energy. There was some initial speed, and then it went up to some final speed. And the difference between those two numbers is the amount of work that was done on the object. In this case, it's the whale, moving its tail. There's a common factor of 1/2 m, which leaves me just v squared minus v2 squared minus v1 squared. So that's the only thing I put in there. Do that calculation, and then multiply by 1/2 times mass, and then get your final answer. So again, pause the video, get that info in. As you're going though, you can see that the 12.8, when you square it, like squaring a bigger number makes it grow faster. So you can see that it requires more and more energy to move something that's already moving quickly, requires more and more energy to move something that's already moving quickly. A shuffleboard player wants to slide a 430 gram disc precisely 12 meters. If the coefficient of friction is 0.62, calculate the initial speed at which the player must release the disc. So again, work is equal to the change in kinetic energy. In this case, we want the disk to stop moving, so its final speed is 0. Remember, change in kinetic energy is 2 minus 1, so that means we have 0 minus EK1. And then we have friction, is the force of friction is the thing being supplied to do the work. And friction results in a negative work. So that way the cos theta is 180 right here. Cos theta is 180, so cos of 180 is minus 1. So that's why it's canceling out with the right-hand side there. And all I did from here was rearrange and solve for v. Multiply both sides by 2, divide both sides by m, square root, and then I get my value for v. And you can just make your substitutions in there from your givens. Don't forget to convert your mass into kilograms. Very good. And finally, we have a situation where we have a police car that's going to speed up, and we want to know what the initial velocity was. So we increase to a speed of 33 meters per second, and that results in this much work being done, 3.1 times 10 to the 5 joules. Again, we set our problem up the same way here, noting that we're solving for V1. And so if I want to start rearranging this equation, I have the work on the left-hand side going to the work on the right-hand side. So I'm subtracting from both sides. I'm going to add the 1/2 mv1 squared to both sides. And then it's just a matter of rearranging for v1. I'm going to multiply both sides by 2, divide both sides by m, and now you're ready just to sub all your values into the formula. I think that's it. I try to keep this video short. You're going to probably need to go back and pause or rewatch things. But I am going to post this note as well so you can have it if you are absent and just need to fill in the values that are missing. Thanks. Good luck.